All right, so today we are going deep, really deep, into the world of nanomaterials and nanostructures. We've got some fascinating research papers here, and our goal today is to basically distill out the most interesting parts, the key takeaways, and give you a shortcut to really understanding this complex and really important field.
That's right. Yeah. We're talking about materials that have at least one dimension, length, width, or height in the nanometer scale.
And a nanometer, help me out here, how small are we actually talking?
So a nanometer is 1/1000th of a meter. Hard to visualize, right? But imagine lining up 10 hydrogen atoms or about 5 silicon atoms, and that distance, that's roughly a nanometer.
Wow. So we're talking operating at the level of individual atoms, right?
Yeah.
And just to be clear, this isn't something brand new, is it? I was really surprised to find out that nanomaterials have actually been used for centuries.
Right. I mean, think about it. That beautiful ruby red color in ancient Chinese porcelain, that's from gold nanoparticles.
No way. Seriously.
Yeah. Or the metallic nanoparticles in Roman glass that give it that shimmering effect. Even some of the vibrant colors in medieval cathedral windows.
So it's not the use of nanomaterials that's new. It's our understanding of them and our ability to manipulate them that's changing everything.
Exactly. I mean, we can now actually see and manipulate things at the atomic level. And that's what's driving the current interest in nanotechnology.
So what's fueling this explosion of interest?
Well, one of the biggest factors is the relentless miniaturization in the semiconductor industry.
Moore's law, right. The one about transistors doubling every 2 years or so.
Yep. And to keep that going, to keep making our devices smaller and more powerful, we need nanotechnology.
Okay, so we're talking about materials that are unbelievably small. But it's not just about size, is it? These materials have completely different properties at the nanoscale than they do in their bulk form, right?
Right. It's not just miniaturization, it's transformation. They can be stronger, exhibit quantum effects, even have lower melting points.
And that all boils down to the increased surface-to-volume ratio, right?
Absolutely. As you shrink a material down, the proportion of atoms on the surface compared to those inside skyrockets. And that surface, that's where a lot of the action is, chemically and physically.
So with such a variety of nanostructures, how do scientists even begin to classify them?
One common way is by their dimensionality, how many of their dimensions are within that 1 to 100 nanometer range. So we've got 3D structures where all 3 dimensions are confined, like tiny crystals.
Okay, so that's 3D. What about 2D?
2D would be something like nanowires, super thin but long. Then there are 1D structures like thin films, which are like, an extremely thin sheet. And lastly, 0D structures. Think individual nanoparticles.
Okay, that's a nice intuitive system. Now, there's also this other classification system I came across, Glider's classification.
Yeah, that one looks at how the nanoscale features are arranged within the material. So you have structures with reduced dimensions. Those are the ones we just talked about, like nanoparticles and nanowires. Then there are structures with nanoscale features only on the surface of a bulk material. And finally, you have bulk solids, where the entire material is made up of nanoscale building blocks.
I think I even saw something about, like, up to 36 classes of nanostructures.
It can get pretty complex. The system looks at all the different combinations of 0D, 1D, and 2D structures you can have. But for understanding the basics, I think those main dimensionality categories are a good starting point.
Got it. So how do these nanostructures interact with, say, light or radio waves? I mean, electromagnetic fields.
Well, it all comes down to scale. When the nanostructure is similar in size to the wavelength of light, for example, you start to see some very interesting size-dependent effects.
Like what?
Like, for instance, in extremely small nanoparticles, you get what are called quasi-stationary fields, where the electric and magnetic fields don't really propagate as waves anymore. And then you've got concepts like dielectric permittivity, how easily a material is polarized by an electric field, and magnetic permeability, how easily it can be magnetized.
And most materials aren't magnetic, are they? I mean, strongly magnetic.
Right. Most everyday materials are non-magnetic. Their permeability is pretty much just 1. True magnetism is a quantum phenomenon, a relativistic effect, actually, related to the spin of electrons. It gets pretty deep.
So what about quantum size effects in something like electrical resistance?
Okay, so you know how in a normal metal, resistance increases with temperature, right? More vibrations, more scattering of electrons.
Yeah.
But in some materials, like bulk bismuth, which has a really tiny band gap, the opposite can happen. Resistance can actually decrease as temperature rises because more electrons get excited into the conduction band. But then, if you make bismuth nanowires or nanolayers, things get weird. Because now the electron's wavelength, its de Broglie wavelength, it becomes comparable to the size of the nanostructure. And that confinement leads to some really unusual temperature dependencies.
So the electrons are basically feeling the walls of their tiny container, and that affects their behavior.
Exactly. So how do we make these nanostructures?
Yeah, how do we make something so small? We can't just carve it down.
Not really. We've got two main approaches, top down and bottom up. Top down is like sculpting. You start with a larger material and chip away at it. But to really get to the nanoscale, bottom up is where it's at. We build things atom by atom, molecule by molecule.
So let's talk about some of these fabrication techniques. What about vapor phase synthesis? How does that work?
So you start with a material in its gaseous state. One method is vapor condensation. Heat up the material in a furnace till it vaporizes, then let it cool down in a different chamber, and bam, you get nanoparticles as the vapor condenses.
Okay, cool. What about MBE, that molecular beam epitaxy? That sounds pretty high tech.
It is. It's basically like spraying individual atoms onto a surface in a very controlled way, like in an ultra-high vacuum. It lets you grow materials one atomic layer at a time with incredible precision.
Like building a material brick by atomic brick.
Yeah, exactly. You can create these layered heterostructures with really sharp interfaces like quantum wells, superlattices, all sorts of complex structures.
And I also saw something called flame pyrolysis. That sounds intense.
Yeah, you use a laser, a powerful infrared laser, to sheet a gas really quickly, causing it to decompose, and those decomposed bits can then form nanoparticles. Very fast, very efficient.
So those are methods using vapors. What about using liquids to create nanomaterials?
So there we have a whole bunch of techniques. You've got precipitation from a solution, that includes things like colloidal methods, sol gel processing, microemulsion.
Right, and electrodeposition too, right? Kind of like electroplating, but on a tiny scale.
You got it. You use an electrical current to drive a chemical reaction and deposit a thin film onto a surface. You can control the thickness really precisely, and you can even create multi-layers by pulsing the current. There's this really cool technique where you use a nanoporous membrane as a template and grow nanowires or nanotubes inside the pores.
That is super cool. And then there's sol gel processing. What is that all about?
You start with liquid precursors, often metal alkoxides that react to form a sol, which is basically a suspension of tiny particles, and then a gel, which is like a cross-linked network. You then dry and heat the gel, and you can get really dense materials with a controlled nanostructure.
Neat. What about spin coating and flow coating?
Those are specifically for making thin films. With spin coating, you put a drop of solution on a substrate, then spin it really fast, and the centrifugal force spreads the liquid out into a thin film. Flow coating is similar. You just pour the liquid over a substrate at a specific angle.
So now we have all these tiny particles, these nanopowders. How do we turn them into something useful?
Yeah, we need to consolidate them, make them dense and strong. But the trick is to do it without those tiny grains growing too large and losing their nanoscale properties.
I can imagine that's quite a challenge.
It is. There's always this tension between sintering, where the particles bond together, and grain growth, where the individual grains merge and get bigger. And a whole bunch of factors come into play. The surface energy of the particles, the presence of any pores, even contamination on the surfaces can affect how well they consolidate.
So are there any advanced techniques for doing this consolidation?
Yeah, there's this technique called field-activated sintering, or FAS. You apply pressure and an electric current to the powder.
Electric current.
Yeah, it helps to remove impurities and activate the surfaces of the particles, which makes them bond together much faster and at lower temperatures. You can get really dense materials with very fine grain sizes.
So how about the mechanical properties of these nanomaterials? I'm curious about their strength.
Well, generally, smaller grains mean stronger materials. That's the classic Hall-Petch relationship. Grain boundaries act as obstacles to the movement of dislocations, which are these defects that allow materials to deform.
So the smaller the grains, the more boundaries, the stronger the material, right?
Right. But there's a twist. If you go too small, below about 10 nanometers or so, you can actually get a decrease in strength. It's called the inverse Hall-Petch effect.
Huh. Why is that?
It's not fully understood, but it probably has to do with the way those grain boundaries start to slide past each other when the grains are really tiny. But anyway, the point is there's this sweet spot in terms of grain size where you get maximum strength.
Fascinating. Okay, let's talk about some potential applications of this technology. Molecular electronics and sensors seem like a natural fit.
Yeah, definitely. With molecular electronics, we're trying to use single molecules to perform electronic functions.
Wow, like a single molecule acting as a transistor or something.
Exactly. And for sensors, we can use molecules or nanoparticles to create incredibly sensitive devices. For example, you can have field effect transistors with a layer of molecules that bind specifically to certain substances. When those substances bind, it changes the electrical properties of the transistor, and you can detect even tiny amounts of stuff.
And I've heard that nanomaterials can also be used to improve energy storage.
Absolutely. We're looking at using them in batteries, for example. Nanocrystalline materials have a high surface area, which can help to increase the energy density of a battery.
I see. And what about those electrochromic devices, the ones that can change color with electricity, like smart windows and displays?
Yeah, so those rely on materials that change their optical properties when you apply an electric field. Nanomaterials like tungsten oxide gels are being investigated to improve these devices to make them faster, brighter, and with better contrast.
And then there are nanoelectronic devices. It seems like that could be the future of computing.
It could be. We're already seeing things like tunneling junctions, negative differential resistance switches, carbon nanotube transistors,
hmm
even single molecule transistors. It's pretty mind-blowing.
The optical properties of nanomaterials must be pretty unique too, right?
Oh, yeah. For example, you have something called surface plasmon resonance in metal nanoparticles. It's basically a collective oscillation of the electrons on the surface of the nanoparticle when light hits it.
And that affects their color.
Exactly.
Hmm.
Gold nanoparticles, for example, can appear red, blue, or even purple depending on their size and shape because of this resonance.
Wow. So we can control the color of a material just by changing its size at the nanoscale.
Pretty much. And then you have quantum size effects in semiconductor nanocrystals or quantum dots.
Yeah, like we talked about with the bismuth nanostructures.
Right. So when these nanocrystals get smaller than the electron's wavelength, the electrons get confined, their energy levels become quantized, and that strongly affects how they absorb and emit light. You can literally tune the color of a quantum dot just by changing its size.
Amazing. And what about these nanoporous materials? Those sound like they could be useful for all sorts of things.
Oh, yeah. They have a huge surface area, which makes them good for things like catalysis, separation, even energy storage. There are a lot of different ways to make them, but one common method is to use templates. You basically create the porous structure using a template, and then you remove the template, leaving behind the porous material.
Cool. And what about those quantum wells in semiconductors? That sounds pretty complex.
It's basically about confining electrons in a very thin layer of material. So you have a sandwich structure with a thin layer of a semiconductor like gallium arsenide sandwiched between two layers of a different semiconductor like aluminum gallium arsenide. This creates a potential well where electrons can be trapped.
And by controlling the size of that well, we can control the energy levels of the electrons.
Exactly, and that affects how the material interacts with light and electricity. And another really important concept is the density of states, which basically tells you how many electronic states are available at a given energy level. And guess what? The density of states is very different in these low-dimensional systems compared to bulk materials.
Okay, let's talk about carbon. Carbon nanomaterials seem to be everywhere these days.
Carbon is amazing. It can form all sorts of different structures, all with different properties. We've got diamond, graphite, fullerenes, nanotubes, amorphous carbon.
And all because of how carbon atoms can bond with each other, right? Single bonds, double bonds.
Exactly. And the different ways those bonds are arranged lead to different structures and different properties.
So, like, what are fullerenes? I've heard of buckyballs.
Yeah, buckyballs are a type of fullerene. Fullerenes are these closed cages made entirely of carbon atoms. The most famous one, Buckminster fullerene, or C60, is shaped like a soccer ball. It's got 12 pentagons and 20 hexagons, all made of carbon atoms.
It's amazing how nature creates such perfect structures. And then there are carbon nanotubes. Those seem to have endless potential.
Carbon nanotubes are basically rolled up sheets of graphene. And depending on how you roll that sheet, you can get different types of nanotubes with different electronic properties. Some are metallic, some are semiconducting. They also interact with light and vibrations in really interesting ways that depend on their structure. And their electronic properties, well, they're really unique. Like the density of states near the Fermi level is very different in metallic nanotubes.
Okay, back up a bit. What's a phonon spectrum?
Oh, sorry. That's just a fancy way of talking about the vibrations of atoms in a material. And the phonon spectrum of carbon nanotubes, well, it's similar to graphite, But because nanotubes are one-dimensional, their density of phonon states, or DOPS, shows some unique features. It has peaks that correspond to specific vibrational modes of the nanotube.
I see. So can we see these vibrations?
You can't see them directly, but we can measure them using techniques like Raman spectroscopy.
Cool. And I also read about electron interference in carbon nanotubes, the Aharonov-Bohm effect. What's that all about?
Yeah, that's a purely quantum effect. It shows that the path of an electron can be affected by a magnetic field even if the electron never actually passes through the region where the field is. It's all about the wave nature of electrons.
Mind-blowing. And what about superconductivity in nanotubes? Is that even possible?
Well, in theory, yes. It's predicted that carbon nanotubes could become superconducting at very low temperatures, maybe a few Kelvin. There's even some speculation about achieving higher temperature superconductivity in carefully designed nanostructures, but that's still very much in the realm of research.
Carbon nanotubes are also supposed to be incredibly strong, right?
Yeah, they have incredible tensile strength and stiffness along their axis. Their Young's modulus is really high, but they can also be brittle, especially the zigzag type. If you stretch them too much, they can develop defects and break. Multi-walled nanotubes, though, those can be super plastic at high temperatures, meaning they can deform a lot without breaking. And bundles of nanotubes, they have anisotropic properties, super stiff along the tubes, but much less stiff in other directions.
So a lot of potential for strong, lightweight materials.
Absolutely. Great for composites and all sorts of applications. And they can vibrate at really high frequencies, too.
Like how high?
Gigahertz frequencies. They have these whispering gallery modes that can resonate with microwaves. You can even use microwaves to make them move or heat up.
So we're talking about nanotubes that could act as tiny sensors, actuators, or even resonators in nanoscale devices.
Exactly. And then there are nanothors, these ring-shaped structures made from nanotubes. They could potentially be used for things like cyclotron resonance, electron acceleration, even generating localized magnetic fields.
So it's not just carbon, right? There are nanotubes made from other materials too.
Yep, there's a whole growing family of non-carbon nanotubes. You've got ones made from polymers, from carbides, even gallium arsenide nanotubes have been made. And silicon carbide nanotubes are interesting too because of their potential for high-temperature applications.
So all sorts of possibilities. I also read about a carbon nanotube-based voltage inverter. Is that like a basic logic element for a nanocomputer?
It is. They basically made a NOT gate, a fundamental logic element, using a single carbon nanotube. It's proof that you can make working electronic circuits at the molecular scale.
Wow. And what about nanowire lasers? Are those actual lasers made from nanowires?
Yeah, you can make a laser from a 2D array of semiconductor nanowires. The nanowires act as both the optical cavity and the gain medium. And they can have really low thresholds and operate in a single mode, meaning they produce a very pure beam of light.
And then there are photonic crystal lasers. Those sound pretty cool too.
Photonic crystals are these periodic structures that can control the flow of light. They can create photonic band gaps, which are basically ranges of frequencies that light can't travel through.
So you can trap light inside them.
Yeah, and if you introduce defects into the crystal, you can create localized modes where light can be trapped and amplified. That's how a photonic crystal laser works.
I see. And finally, there are these crazy metamaterials and something called left-handed matter. What's that all about?
So metamaterials are artificial materials that get their properties from their structure rather than their composition. They can do all sorts of weird things with light. And left-handed matter, well, that's a hypothetical type of metamaterial that would have a negative refractive index.
A negative refractive index, so light would bend the opposite way.
Exactly. It's pretty wild stuff. And some people think that carbon nanotubes, because of their helical structure, might naturally exhibit some of these left-handed properties. But we're still figuring all that out.
So we've talked about making these materials and their amazing properties, but how do we actually see and manipulate them at such a tiny scale?
We use tools like scanning probe microscopy and atomic force microscopy. AFM, for example, uses a tiny tip to scan the surface of a material, and it can create images with atomic resolution. You can even use it to manipulate individual atoms and molecules.
It's like a tiny finger that we can use to feel and move things at the nanoscale.
Exactly. And then you have MEMS and NEMS, microelectromechanical systems, and nanoelectromechanical systems. These are basically tiny machines with moving parts that are made using techniques similar to those used for making computer chips.
Fascinating. And then there's self-assembly. This seems like the ultimate bottom-up approach, right? Things just spontaneously forming into ordered structures.
It is. We use self-assembly to create thin films, ordered arrays of nanoparticles, all sorts of things. One common example is using surfactants to create self-assembled monolayers, or SAMs.
And what about those core shell nanostructures? It sounds like you're basically putting a coating around a nanoparticle.
Yep, that's exactly what it is. You can have a metal core with an oxide shell, or a semiconductor core with a polymer shell. Lots of different combinations, and it lets you combine the properties of two different materials in a single nanostructure.
So many possibilities. And with nanomanipulation and nanolithography, we can even pick up and move individual nanostructures or draw patterns at the nanoscale, right?
Exactly. We can use tools like AFM to manipulate things and create structures with incredible precision. And then, of course, once we've made these materials, we need to characterize them, figure out what they're made of, their structure, their properties. We use a whole suite of techniques like X-ray diffraction, electron microscopy, and spectroscopy.
A whole arsenal of tools to probe the nano world. We talked earlier about the enhanced strength of nanomaterials. Is that all because of the lack of defects?
It's a major factor. Because nanowires and nanorods are so small, they tend to have fewer defects, like dislocations. And bottom-up synthesis can also lead to fewer surface defects. So you end up with these incredibly strong materials. But it's not the whole story. The way those grain boundaries interact with each other also plays a role.
Okay. And what about quantum conductance in nanowires and nanotubes? Is electricity flowing differently at these tiny scales?
Yeah, it is. At the nanoscale, the conductance of a wire can become quantized. It can only take on specific, discrete values. You also get this thing called Coulomb blockade, where it takes a significant amount of energy to add even a single electron to a tiny nanostructure. And that's actually the principle behind single electron transistors.
Wow. And nanobots? Are we anywhere close to having tiny robots doing cool stuff?
True nanobots, like the ones you see in science fiction, those are still a long way off. But we are making progress towards creating nanoscale devices that can perform specific tasks, like delivering drugs or acting as sensors.
What about catalysis with gold nanoparticles? I always thought of gold as being pretty unreactive.
It is in bulk form. But gold nanoparticles, especially when they're deposited on certain supports, they can be amazing catalysts for a whole range of reactions.
Why is that?
The high surface area and the unique electronic properties of gold nanoparticles make them very reactive at the nanoscale. And their catalytic activity is strongly dependent on their size and shape, so we can tune their properties for specific applications.
So we can control chemistry at a very precise level using nanoparticles.
Exactly. And then we have nanomechanical sensors. You can use AFM cantilevers as incredibly sensitive detectors of force or mass. By coating them with specific molecules, you can make them sensitive to specific things, like viruses or bacteria.
Like tiny scales that can weigh individual molecules. Amazing.
And carbon nanotubes, well, they're good field emitters. They can emit electrons when you apply a voltage.
And why is that useful?
It could be used for things like high-resolution displays, electron microscopes, even new types of light sources. And finally, we're using nanostructures to improve solar energy conversion in photoelectrochemical cells.
Because of their high surface area.
Right.
More area for light absorption and charge separation.
Exactly. So as you can see, nanomaterials have the potential to revolutionize a huge range of fields.
It's incredible how much we've learned about the nano world in just a few decades.
Yeah, and we're only just scratching the surface.
That's a good way to put it. So some of the things that really stood out to me were those ancient examples of nanomaterials, the fact that strength can actually decrease at very small scales, the possibility of superconductivity in nanotubes, and those mind-bending metamaterials. It's clear that we're just beginning to understand the potential of this field. So what are some of the big challenges that researchers are still working on?
Well, one big challenge is control. We need better ways to control the size, shape, and composition of nanomaterials.
So we can really fine-tune their properties.
Exactly. And we need to figure out how to scale up production. Right now, a lot of this is still done in the lab. And then, of course, there are the safety and environmental concerns that need to be addressed.
Of course. We need to make sure this technology is developed responsibly.
Absolutely.
Well, this has been a truly fascinating deep dive. It really makes you wonder what other amazing discoveries and inventions await us as we continue to explore this incredibly tiny yet incredibly powerful world. Thanks so much for joining us.